I'm your host today, so good afternoon and good morning to our participants, and thank you for attending this session with DeltaTek. We've got a fantastic number of attendees today from all over the world, and I'm sure that our hosts won't mind me saying, but they're delighted that you've taken the time to join them today. Over the next 45 minutes or so, you will hear from both our hosts, Tyler and Tristan, from DeltaTek. The webinar will look at DeltaTek's revolutionary Cure technology range and explore how they've provided value-adding well construction solutions to operators globally. But before I introduce both of our speakers, I want to run through a couple of housekeeping issues. So first off, your mics will all be muted automatically, but if you could just double check that you're still muted and that remains the case throughout the duration of the presentation. If you have any questions, there is a Q&A function on the bottom panel of your screen. Feel free to put any questions that you have in there and we'll answer them towards the end of the presentation if there's time. Please bear in mind that we might not get through all the questions today, but both of our speakers will be delighted to answer any questions offline, and contact details will be provided to allow you to contact them. Lastly, we are recording this session, so you will receive a copy of it afterwards to view at a later date. So without further ado, let me introduce you to our speakers. Our first speaker today is, well, maybe not our first speaker, but our first host is Tristan, who graduated with a master's degree in engineering. He's steadily progressed through various drilling engineer and supervisory industry roles at various operators, and having identified various problems in the well construction industry and gaps in the market, at 31 years old, founded DeltaTek in 2015. This led to the development of SeaCure, an industry-first technology. Tyler is our BD manager in the Western Hemisphere, based in Houston, and has a degree in mechanical engineering and over a decade in professional experience in the oil and gas services industry, including a number of international placements. He started his career in design engineering and in field applications engineering before transitioning into business development and general business management roles. Tyler is currently supporting DeltaTek's expansion into the Western Hemisphere, as I say, based out in Houston. So welcome to you both. We're going to kick off today's webinar with a short video before handing over to Tyler to talk about our technology.
All right, thank you.
DeltaTek is a well construction specialist supplying novel technology solutions to the drilling industry. Low risk, high value technology. That, in a nutshell, is what DeltaTek provide, and has done so with proven rig time savings to enable lower cost of drilling operations. That's lower financial cost, lower risk cost, and importantly, lower carbon cost.
DeltaTek has become a well-recognized name in the oil and gas industry, probably best known for its SeaCure technology, which has been rapidly adopted across the North Sea since its initial deployment by Chevron and Siccar Point Energy in 2018. Since these early days, DeltaTek have developed multiple low-risk technologies to further reduce its customer well construction risks, saving rig time and adding value in the process. DeltaTek now deploys its SeaCure and Articulock technologies across the globe, from the depths of the Southern Oceans all the way to the Arctic Circle.
Since our first deployment back in 2018, I'm happy to say we've come a long way and are about to do our 20th deployment. Our customers have shown great acceptance of our technology, mainly due to its simplicity and the value it brings. I'm also happy to say that since our first deployment, we've maintained a zero NPT. Our customers have been very engaged and really helped us develop from our first technology into what we have today. And I'm happy to say they also come back for the second and third operations, which is a testament to the simplicity of our technology. We have gone from humble beginnings here in the North Sea to having deployments in the southern tip of Africa, the eastern Mediterranean, and now most recently up in the Arctic Circle. And very soon we're about to go west.
DeltaTek offers a step change in well construction efficiency and has developed solutions that reduce carbon costs. That means that our customers benefit from supporting net zero targets without being penalized on a cost or efficiency basis.
We've gotten verbal confirmation from the client, working towards a 2-year contract and working out some of the technical details with their wellhead running tool provider this afternoon.
DeltaTek does exactly that, supplying intelligent, time-saving, cost-lowering, risk-mitigating technologies that concurrently reduce our customers' impact on the environment from the earliest stages of the well's life cycle.
Okay, Tristan, got the confirmation from the hotel in Hammerfest. Your guys is heading up there, I think tomorrow, the 19th. Everything is ready for the next operation up in Balancey.
DeltaTek and the Cure service line has delivered up to 70% weight on cement time savings, reduced carbon emissions and supporting net zero goals at no additional cost, provided the best available and safest technology for wells. For more information about DeltaTek and its revolutionary services and technology, please visit deltatekglobal.com.
So again, everyone, good morning, good afternoon, wherever you are. I'm Tyler Reynolds, and it's my distinct privilege to introduce SeaCure, the company's flagship technology as inner-string cementing, stabbed-in inner-string cementing for subsea wells. So to introduce this topic, we've got a video here that will play recapping one of our white mat demonstrations, which has been really well received across the customer base, folks that we've been talking to over the last year. And we've cut in some videos of rig footage and operations to further demonstrate the points that we make here. For this demonstration of the SeaCure cementing system, we're looking at a riserless section, such as a cemented conductor or surface casing, for which a SeaCure compatible float shoe will have been pre-ordered with requisite latch and adapter and potentially lockdown wiper plug receptacles. Once the casing's been run and hung off at the rotary table, we're ready to run inner string. The first thing that's picked up is a SeaCure BHA, comprised of our latch and adapter, weight set sub, and SeaCure slip joint tools. This BHA is 30 feet long in its closed position. Once it's picked up, the SeaCure tool strokes open under its own weight to lengthen the assembly to 40 feet. This 10-foot of stroking distance is what allows you to approximately space out your inner string within the casing bore. The SeaCure BHA is run into the casing on drill pipe until made up to the cam actuated running tool. Inner string is then lowered until the latch and adapter engages, which is confirmed with an overpull. As the running tool is established, the SeaCure tool strokes partially closed. Upon closing just 4 inches, the SeaCure tool's internal clutch mechanism disengages to allow free rotation of the inner string along with safe makeup of the cam actuated running tool. It's important to note that the running tool's ball valve is left open for the duration of the SeaCure cement job due to the hydraulic seals affected within the float shoe at the latch and adapter. At this point, the casing can be run to cementing depth and primary cement job pumped. At the end of the cement job, a lockdown wiper plug can be launched into the string and chased with slurry to guarantee good quality cement around the shoe. It's important to note that the lockdown wiper plug affects a bidirectional seal after it bumps because of a ratchet mechanism built into the nose on the plug and corresponding receptacle in the shoe. Subsequently, pressure is applied to the inner string to actuate a burst disc that's been pre-installed within the latch and adapter here. Once this burst disc ruptures, the remainder of the inner string contents can be circulated out via the inner annulus and vented to seabed. The running tool's ball valve can then be closed by ROV to enable a life of well integrity casing pressure test immediately after pumping the cement job. Importantly, this test can be completed against green slurry in the borehole annulus, mitigating the risks of weakening the cement bond and creating a microannulus due to the radial expansion of the casing under pressure. It's also possible at this point in the job to introduce our patented quick cure process.
The QuickCure process utilizes a pit of seawater that's been preheated on the rig to approximately 65 degrees Celsius or 150 Fahrenheit. This heat sweep is then rapidly circulated into the inner annulus. After the casing bore has been filled with the heat sweep, a maximal exit temperature is observed on an analog temperature gauge that's been pre-installed on the running tool's ball valve. At this point, the ball valve can be closed to allow the additional heat to soak through the casing wall and into the slurry. The additional heat causes a rapid build in compressive strength while reducing weight on cement time by up to 70% and improving transition time up to 50%. As an option for most SeaCure jobs, a ball drop activation mechanism can be utilized in lieu of the lockdown wiper plug. There are a few key procedural differences for the ball drop version of SeaCure. Once the primary cement job has been pumped, instead of launching a wiper plug, the SeaCure ball is dropped into the inner string after displacing the cement job within a few barrels of the shoe. The SeaCure ball starts its life as a 1.75-inch tungsten core. It's built up to 1.9 with an NBR coating, seating within a 1.88 counterbore in the ball seat that's been pre-installed in the latch-in adapter, roughly 14 inches off the nose. The ball gravitates down and lands within its seat. After pressure is applied, a half-inch packer-style seal is affected in the NBR coating. It's important to note that a no-go shoulder has been designed within the ball seat to ensure the ball can be retained. The remainder of the process is the same for the ball drop version as the lockdown wiper plug version, in that pressure is applied to the inner string until the burst disc is ruptured, and the remainder of the inner string contents are circulated out through the inner annulus, and subsequent pressure testing and/or QuickCure processes can be implemented. However, one unique aspect of the ball drop version of SeaCure is, because of the positioning of the ball seat within the latch-in adapter, 14 inches off the nose, for jobs that wait on cement, it's possible to retrieve a down-hole sample of cement from the shoe itself. We call this feature Core Cure, an albeit qualitative but definitive example of the quality cement you have at the shoe. The remainder of the SeaCure process is identical for any of the versions selected. Because the SeaCure tool is still in free rotate mode, the cam-actuated running tool can be disengaged and picked up safely. The last 4 inches of stroke open on the SeaCure tool engage its internal clutch to allow through rotation and for the latch-in adapter to be released through a J-slot mechanism. Alternatively, a backup shear-out sleeve built into the float shoe allows a designed overpull to release the inner string. Once the inner string has been retrieved, you're left with a clean casing bore, and importantly, no shoe track to contend with.
Okay, so with the conclusion of that explainer video for how the system works, we've got some further slides that will go through a few other details, and including the main value statements for why customers are selecting SeaCure, elaborating on some of the points made within that video. So Tristan and Jamie, please let me know if there are any issues with hearing me or seeing the screen, and Tristan, feel free to jump in to contribute to these comments if needed. So what is SeaCure? Again, stabbed in inner string cementing for subsea wells. And some of the points that we like to make regarding the service is that the only long lead item associated with it is the float shoe or float collar, depending on the application. And we've got intellectual property that provide for a non-exclusive OEM. So basically we can work with any of the float equipment providers according to customer preferences, and that includes latch-in or tag-in versions of the float shoes or collars. So another point that we like to make is that the latch down plug receptacle that was explained in the video has a 5,000 psi or 7,500 psi rating, depending on the material selected for that plug receptacle. And some special configurations for different applications include an autofill version we call SeaCure, as well as a leading mechanical or multi-mechanical interface option called Cure Catcher, for which we can drop in foam balls, you know, in accordance with the need to provide mechanical interfaces between the cement slurries and spacers and displacement. What you see on this slide is an actual loadout basket for one of our jobs, and it constitutes the dual string or multi-well loadout, for which you see, you know, multiple SeaCure tools already pre-made up, and centralization, and, you know, all of the bits and pieces that we need to complete the job. So the point being that, you know, we can service multi-wells or multi-strings with just a nominal list of equipment that we can fit in one of these 40-foot half-height offshore baskets. So that leading into why SeaCure and the main value statements, some of which were represented in that video, but we try to be comprehensive in communicating the value that we see and our clients reinforce for this system, and falling into three kind of main categories of saving rig time, operations efficiency, and risk mitigation benefits. The first one being saving rig time, which is also the company's motto. And this is primarily brought through eliminating the shoe track in the most efficient form of a SeaCure job. You know, in kind of the biggest value statement around eliminating a shoe track is eliminating a corresponding dedicated cleanout trip. This is especially relevant for a bigger step down in size, like with the slim hole well design. As you can see, this case study, which we'll review in detail for Chevron in the UK North Sea, they drilled out a 30-inch shoe with a 12.25-inch assembly, which prior to using SeaCure required a 26-inch cleanout run. So we saved kind of a minimum 8 hours of rig time savings there. But in addition, when you look at just comparing the time taken to drill out a conventional pour buoy shoe track of 100 to 150 foot axial length versus SeaCure, giving you just a neat little 3-foot shoe to drill out with an easy to drill out tapered centralized shoe design. Our shoes drill out in, you know, typically 20 minutes, but the quickest being 6 minutes, versus the what our customers routinely report is a 4 to 6 hour typical drill out time for a pour buoy shoe track. Another opportunity to save rig time looks at the radical reduction in weight on cement time savings that we can bring through our quick cure process, which was presented in detail in the white mat demonstration. But again, this is the opportunity to circulate a heat sweep of fluid within the inner annulus between the drill pipe inner string and the casing bore to apply additional heat to the slurry in the borehole annulus. And what we've been able to prove is a 500% compressive strength improvement in 12 hours relative to ambient temperature curing. And we've got a case study that again we'll go into more detail, but on 6 wells for CNOC AGR in the UK North Sea on the Buzzard field, we were able to reduce weight on cement time from circa 13.5 down to 4 hours. So 9.5 hours rig time savings per well. And I'd just like to interject, reinforcing what Jamie announced at the top of the webinar, and that we really want to get your questions. If you have any questions regarding any of this material, we'd love the opportunity to answer those kind of at the conclusion of our slides. Something that constitutes an obvious question is like, how do we create the heat sweep on the rig? And DeltaTek's philosophy in all of our technology, and certainly exemplified here, is that we try to implement a right size solution in the simplest configuration possible. So we're typically just circulating a pit of seawater through the high pressure mud manifolding shear gun lines to heat it up to 60, 65 degrees Celsius. And what you see here in these photos is where we were able to complete that work for 500 barrels of seawater in advance of the cement job. And these photos here show the temperature gauge that's been pre-installed on the running tools ball valve, snorkel valve, that the ROV can just fly over and witness as the heat sweep is being placed and filling the inner annulus in the casing. And then another thing to elaborate on is that we actually provide a controlled temperature bath at the rig. Our offshore technician will utilize the temperature profile as observed here for the heat sweep coming out of the running tools ball valve to replicate like what that additional temperature will provide to the cement samples that are taken out of the mix unit. So we're able to provide those samples to the company man as that qualitative check. What this shows for QuickCure is UCA laboratory testing and comparing the same cement sample between conventional or ambient temperatures versus SeaCure that includes the heat sweep effect. And we've drawn some lines on the plot so that you can see in a little bit better detail considering the axes on these charts. But the brown line representing the compressive strength development for the slurry. And again, like there's no difference between the cement sample between these two tests. It's just introducing the QuickCure temperature profile, which is this series that hopefully you can see my mouse riding upon. But there's an elevated temperature there provided by QuickCure, for which the brown series, you can see that the 500 PSI threshold for compressive strength development was reached with ambient temperatures at 11 hours versus just 4 hours for the QuickCure sample. So that corresponding to roughly 70 to 90% weight on cement time reduction depending on the heat sweep input temperature. Moving on to operational efficiency, and this being the second bigger category for the value statements that SeaCure provides, is SeaCure is in general the most flexible and efficient placement method for your cement job, in giving you the opportunity with the stabbed in inner string interface to eliminate this slug of cement that would constitute the poor boy shoe track. And with a lead and tail design, you save this volume of cement potentially twice. So this can be multi-hundreds of barrels of cement depending on the design criteria for the string and the size and so forth. But also, just because you had the opportunity to witness cement returns to seabed earlier by a couple hundred barrels, you have the opportunity to move to displacement and to reduce the potential for a big patio to occur and the additional time taken to deal with that, as well as providing an obvious environmental benefit. So looking at environmental benefits as a point of note, we've got a case study that I believe Tristan will review in a bit more detail, where we very clearly demonstrated a few hundred barrels of cement saved for one of our operator customers. And upon publishing a case study that highlighted the net zero goal improvement based on this cement savings, we got some recognition from the OGA there in the UK for contributing to net zero technology. The final bucket here for risk mitigation being arguably the most valuable part of the process, and why most of our customers are coming back to use SeaCure again, is that in general, you get a better cement job. You know, you've got a lot lower displacement volume through this relatively tiny inner string versus, you know, certainly the plug set, you know, where you would have a full bore displacement for your cement job. There's less contamination potential, and we can prove that you get a good quality cement job through the likes of our core cure sample that, you know, we covered in the white mat demonstration, but you can see here in the slide, these cores being actually taken out of the latch and adapter. Additionally, as in the white mat demonstration, the casing pressure testing for surface casings is a unique aspect of SeaCure as an inner string cementing setup, but providing a post-cement job casing pressure test, in situ casing pressure test, immediately after the cement job is pumped. And because you're able to complete that pressure test against green cement, it reduces the potential for a microannulus or weakened cement bond. And you've also got an opportunity that you see in the bottom right. This is one of our customers had the opportunity on a dual derrick setup to actually plumb into the running tools ball valve prior to running the casing and to complete a 500 PSI casing pressure test before they ran the casing, which is a unique capability for SeaCure that if you had the opportunity, it's a nice confirmation that all the connections have been made up successfully, and that, you know, forward operations, you can have some certainty that that wouldn't introduce the leak path if it were observed. So all of this is, you know, with the intent of reducing the event like this happening. What you can see on the left here is was published early this year, showing that an operator in the Gulf of Mexico had a failed surface casing pressure test, and they had to call out one of these big bore packers and spent a fair amount of time, a couple of days in PT, establishing the leak path for that surface casing. And so SeaCure provides the capability to complete this pressure testing immediately after the cement job, and therefore off the critical path prior to running BOP, to enable you to react and to save, you know, a costly event like this. Additionally, for risk mitigation, you know, we've got the point that we're mitigating drill bit and BHA damage, as well as reducing casing ID damage. And we've got a very short case study here illustrating this point, where one of our clients had a 12¼ inch drilling assembly that was pulled for an MWD failure on stand down after drilling out the shoe and shoe track. And what they observed when they pulled the bit is that they had broken gauge cutters on the PDC bit. And subsequently to the following run, they ran a caliper to ascertain the open hole and the casing shoe track ID. And what they saw is that actually the casing ID within the shoe track interval was enlarged slightly. And there's a calculation table here for how much steel they actually introduced into the borehole as swarf, which you can see here, one of the pieces of swarf returned there at the rig. So what it highlights is that, you know, drilling out the shoe tracks, you know, the parameters they used and what they observed from a drilling dynamics wasn't unusual. And, you know, the potential there to damage your bit, potentially vibrate and damage your BHA, and damage the casing ID is greater if you have to drill out a cement shoe track than if you don't have one. So with SeaCure, you're giving your bit the best chance for suction TD, as well as mitigating the other kinds of damage that you can see in this case study. So as a one-page kind of recap of all these points that we hand out, you know, as a handout for our presentations, you can see all of these value statements listed here, and highlighting that SeaCure is just, it's more than just eliminating a shoe track and saving some rig time. It's quite a lot more. And with that, I'm going to hand back over to Tristan and allow him to continue the presentation here.
Tyler, thank you very much. Hopefully everybody can see my screen now. Tyler, can you just confirm that before you?
Gotcha.
That's great. So yeah, just echoing the thanks for everybody's participation. Got a lot more participants than I anticipated we would get in my experience of these, so very grateful for that. And hopefully we can keep your engagement throughout the final sort of 15-20 minutes of this, whilst I take you on a short journey about where we came from and through the sort of milestone of where we are right now with our 20th deployment of Cure systems. Because yeah, right now we've got equipment all over the show. We have you know, a globally servicing team, and it's not always been like that. In fact, it was only 2 years ago that we were a team of 3 people in DeltaTek. And on an OGTC supported project, we were doing the inaugural deployments of our SeaCure cementing system. So yeah, only 2 years ago. But before we get into the real journey, I just want to put a small overview of what we've managed to achieve over these few years. So on the left, you can see a representation of the customers that we've worked with. And it's quite the extensive array of customers, which we're real proud of. And on the right, what we can see is an experience radar, where each one of the 5-sided lines represents a single deployment of our SeaCure cementing system, with different technical difficulty parameters, as we refer to them, either water depth, casing length, how long the tools are downhole, how much cement has been pumped through the system, and how much pre-circulation fluid volume has been pumped through. And what you can see about the technical difficulty radar that we've managed to pull together over the 20 deployments is that it is all-encompassing. It's very expansive. We're approaching water depths of 2 kilometers. We've got over 1 kilometer of casing under our belt. And these are reputed to be the biggest cement jobs in the world, 3,500 barrel cement jobs, real monsters. But we're really proud that our system across all of these deployments has yielded a 0 MPT outcome with value add, which we're grateful for. So yeah, so skipping back to that 2 years ago, 2018, 3 of us in DeltaTek and an OGTC sponsored project with Chevron and Siccar Point Energy. We did the first runs of SeaCure. This particular case study, which I'm presenting here, is the subsea deployment, which was actually preceded by 2 onshore deployments of 9 5/8 SeaCure systems. Following the perfect results on those 2 jobs, we recognized that the growing hype around the service and the technology meant that the team of 3 that we were in DeltaTek at the time was not going to be sufficient to service that properly. So we recruited our first non-director employee in the summer of 2018, Chris Johnston, who's now our esteemed operations manager and has a team of operations supervisors reporting to him. But it was Chris and I that went to the Ocean Guardian in September 18 on the last well it drilled to do this first subsea deployment of SeaCure, which really laid the foundations for what has become this very well adopted and market accepted technology now. So not only was it a good success that we did that there with a blue chip customer such as Chevron, but it also yielded a huge amount of value. Tyler referred to the fact that with SeaCure there is no internal shoe track, which means that there's no sheath. So when drilling out slim hole, there is no need for a clean out run, and that's what Chevron enjoyed, saving 8 hours of rig time in that deployment. Now the OGTC project that created this was a concurrent one with Siccar Point Energy. So that was our next deployment. Siccar Point Energy's west of Shetland well, Blackrock. And this was another world first, the first time ever that downhole cement samples had been recovered from a string being cemented. Our core cure service, so you can see that in the bottom photograph there. So that kind of concluded that OGTC project and put another, really successful deployment on the belt of SeaCure in what was approaching quite deep water, over 1 kilometer of water. And the really nice thing about this deployment was that not only was it our second subsea run, 4th deployment, this was actually concurrently happening with a major operation in the Eastern Mediterranean at the same time. So Chris was back out to the rig to single-handedly manage this deployment, whilst myself and our newly recruited operations supervisors of Jonas Tavern, Vernon Hay, and Chris Cadiz were down in the Eastern Mediterranean on the Drill Max, doing some real deep water work on surface casings with Energy-N. So the team were actually, we actually had to split the team at a certain point during the batch campaign here in order to bring Vernon and Chris back to go and do another job in the UK. So the sort of picture I'm trying to present here is that the adoption of this technology was really quite impressive. We actually went from first deployment with Chevron to doing 30% of the new subsea wells in the UK within just 9 months. You know, a massive accolade. And this particular deployment really stretched that operational envelope, giving customers that confidence that, you know, this system is reliable, it is capable of delivering what they want it to do. And this is still, I believe, the current standing record for drill out of the SeaCure system. So just a 6-minute drill out, which is, you know, significantly quicker than what normally happens. So that other concurrent deployment that was happening back in the UK was one for Total, another, you know, major customer. This one was for a surface casing where clinical execution cement placement was required. The conductor in this instance was a conductor, and so not having a significant patio of cement across the top of that structure is important for its operation. This SeaCure selection here meant that clinical execution was what Total enjoyed. So yeah, really proud of the fact that, you know, we were doing kind of 3 operations concurrently across you know, West of Shetland, East of Shetland, Eastern Mediterranean, being what was still, you know, just an 8-person, 9-person company at that stage. So you know, it was really kind of stretching our wings and showing our capability as an organization to deliver overseas and locally, and maintaining 0 MPT excellent service execution and growing our customer base. SeaCure Point, after the first job we did with them, were gracious enough to offer us some additional work, and I see we've got some representatives online from SeaCure Point, so great to have you guys here with us today. Thank you again for your custom over the years. Not only were we offered the conductor on the Lion well, but following some complications with the traditional technique of SSR plug cementing on the Blackrock well, we were awarded both the conductor and the surface casing on Lion. So, you know, real nice kind of opportunity to, you know, displace what has been the status quo for decades with this new technology, and you know, knock it out the park, as it were. What this job and deployment yielded was a recognition that it wasn't just about saving rig time or reducing risk or, you know, adding sort of dollar value to the project, but it was also about answering that carbon conscience of the operators, which is becoming more and more prevalent nowadays. This particular job in post-work analysis showed that over 100 metric tons of carbon dioxide were reduced as a direct result of utilization of the SeaCure system. And we're really grateful for the Petrofac team for continuing their work with SeaCure Point and utilizing the service here. And, you know, we're now working within Petrofac with some of the other teams, and we're looking forward to expanding the service delivery across some of Petrofac's other customers. Now, the story with the QuickCure one is one which I'm very proud of. There's a normal kind of understanding that oil field technology, from concept through to commercialization, takes in the order of 8 years on the journey. Now, the QuickCure process was patented in April of 2018. Skip forward 12 months, and we had actually executed 5 successful commercial deployments of this technology on the anniversary. And I remember texting the team, you know, just for a big pat on the back on that day to congratulate the guys who were offshore doing the work, and the onshore team who had been, you know, significant part of that intellectual property and development journey. So yeah, massive accolade here, and we're really chuffed with that rapid adoption of the technology. I wanted to leave this case study in because it's testament to the fact that we experience massive loyalty in our customers, which we are incredibly grateful for. What we normally find is when a customer moves to SeaCure, they stick with it, and we're really grateful for that. This is testament to that, in the fact that Total's first deployment they did with us meant that they continued to use us, and they've continued to use us this year as well on their Fingen well. And they've procured their equipment for future activity with us as well. So we're really grateful for that. And I wanted to pop this one in because you know, everybody's had a bit of a stressful year, to say the least. And you know, we're very proud that Premier, who continued to operate throughout the COVID lockdown crisis, benefited from our service there. on the Transocean Leader during April of this year. New recruit Alex McGill was off to go and cut his wings on that job there, and he's now working on some other deployments, which is great to see. And Premier as a customer have been fantastic, and they're now spreading the use of SeaCure across some of their other assets, namely the senior DSV that was on that operation has been instrumental in pulling SeaCure into his next project. So, just that loyalty is something that we're hugely proud of and grateful for. Lundin, the first operation in Norway of our SeaCure system. This was back to clean out run elimination, delivering zero shoe track surface casing cementation, meaning that undergauge drill out is not a concern. Something that Lundin enjoyed. And following this first job, we're currently away to do the second, and we've received confirmation that their next well will also be using SeaCure. So again, that loyalty is something that comes through here. Once customers move to this solution, they stick with it, which we're grateful for. So I may have demonstrated some of my passion and enthusiasm for our products and services over the last 10 minutes or so, but to be honest, that's nothing compared to what we have here in FloatCure and SeaCure RS. Don't get me wrong, I really chuffed whenever we do more and more value adding SeaCure and QuickCure and CoreCure deployments. But FloatCure and SeaCure RS are true game changers in my eyes, and that of the customers that we've spoken with thus far about them. Again, it uses the exact same zero NPT, highly reliable equipment and technology that we've used thus far, just in a slightly different format. So firstly, FloatCure. So like I say, it's the exact same inner string that we've run time and time again, except in the string that we are SeaCure cementing. Critically, what has happened is when we've been running, in this instance, the liner, after having picked up the shoe track and running the liner joints, you do not top fill the liner. So you run it dry. Thereafter, once the dry string has been run and you're ready to run inner string at the rotary table, that SeaCure inner string gets installed, stung and stabbed into the collar, and the liner hanger assembly made up at the upper end. And what you've then established is a fluid pumping conduit through the inner string, but with a designed air chamber for buoyancy in the inner string by liner ID. And the amount of benefit that this can yield is incredibly profound. The reduction in net effective weight of the string being cemented is in the order of 50 to 80%. So what that means is, typically say a 53.5 pound 9 5/8 liner might only actually weigh 15 to 20 pounds per foot. So when you consider the amount of additional reach that puts on the wells that are being drilled from existing infrastructure, you can suddenly grow your operational envelope from that platform by orders of magnitude. Accessing stranded pools, is one of the huge value benefits that this can do. Saving sections out of wells, which might otherwise have needed 2 sections to reach a particular target, can now be done in 1. This can turn what might have been a subsea tieback into an ERD well from a platform. So its carbon benefits are monumental. And I'm sure you can feel that passion that I have for this technology coming through, because this is game-changing stuff, which we're incredibly proud of. So not just necessarily the torque and drag benefits, but when you consider the fact that you're now cementing with 50 to 80% less effective weight, the standoff that gives to the string being cemented is improved by orders of magnitude, moving what might have been 55 to 60% casing standoff up to 95% casing standoff. So when it comes to delivering the ultimate primary cement job and life of well integrity, to make sure that fewer interventions are needed and you're going to get the most out of your wells, it can't be done any better than with FloatCure. And the beauty of it, it's all with our existing technology hardware. So FloatCure, please do keep an eye on this technology. SeaCure RS, our reservoir system. So this is SeaCure's little brother, as it were. It's exactly the same system in terms of the procedure and the actual technology in respect of the clutch and stroking mechanism, albeit in a smaller size. So this brings this technology to the small liner market, hence reservoir system. So really what we're targeting here is cemented reservoir liners. What's the value? What's the benefit? Well, drilling at well TD can be the most risky few stands of the well that you drill. And sometimes that is simply to accommodate a shoe track. SeaCure RS delivers a zero shoe track reservoir liner, meaning that you either don't need to drill those few stands at well TD, or if you didn't have the luxury of drilling those few stands at well TD, you don't have to do a clean out run after having done the cement job. So, masses of risk saving as well as rig time. The further benefit that SeaCure RS offers is that you are given a work string all the way to well TD immediately at the end of the cement job. So what that means is that once you've set the packer, you can go directly into brine displacements or suspension fluid displacements or whatever you want to do without a further full round trip. So risk plus saving rig time. And on that, I see we're approaching kind of the last sort of 10 minutes for any Q&A. So yeah, please, do come forward with questions, and Jamie, over to you, if that's okay.
Perfect. Thank you very much to both of you. So to round off the session, as we said, we have had a couple of questions come in, and we do have a couple of kind of common questions that tend to come up that Tyler and Tristan are going to be able to address for us. So the first one actually relates to float cure. So Tristan, with float cure, is there any well control risk associated with the circulating of an air bubble around the open hole formation?
Yeah, that's yeah. So the well control conversation is something that we have a lot with customers. It's an really important question because it can be this risk alone, which makes a lot of operators reluctant to utilize the traditional flotation techniques. Buoyancy assist casing equipment, the NCS, the TCO type of flotation collars, which are run prevalently around the world. But some customers, they might not actually do that for the well control risk. Other operators, who do it, they enjoy massive benefit associated with flotation. But one of the many beauties of float cure is that, unlike traditional flotation techniques, which require the operator to manage that air void with the open hole exposed, and that's normally done either through burping the air void back up through the ID, or doing significant pre-circulations of the wellbore prior to cementing with well-controlled devices at the ready because of this risk. What float cure does is it ensures that the cement job is entirely complete with pressure tested isolation barriers in place prior to managing the air bubble. So, and that's achievable because of the lockdown bidirectionally sealing wiper plug, which is installed at the top of the shoe track, and that is fully pressure tested prior to the liner top packer being fully set and pressure tested, whilst the air void is safely contained beneath the liner running tool, the seals of the liner running tool within the hanger. So it's only once these mechanical pressure tested bidirectionally sealing isolation devices are fully installed and pressure tested, that's when the air void is handled safely and with the formation isolated behind mechanical pressure tested barriers. So yeah, really important conversation point.
Mm-hmm. Great. And we actually, I think that these kind of questions are actually starting to start on quite a few more questions. So we've got some are appearing in the chat and some that are appearing in the Q&A box, which is great. Yeah. Any other questions, please feel free to fire them in. Although the webinar was due to end at past, if anybody does want to stay and kind of continue to discuss, Tristan and Tyler are happy to hang about. So the next question that appeared was, again, with float cure, are there any risks of the liner actually floating to high side and creating too much drag at the upper borehole wall whilst running and rotating?
Yeah, good. So, I guess just to summarize the question, can you get so much buoyancy that actually the string floats high side and drags along the top? And the answer is very unlikely. So in about 95% of the applications that we've looked at and modeled with our partners, the net effective weight of the liner is reduced by 50 to 80%. What does that mean? Well, 9 5/8, 53.5 pound liner. What you'd expect to see that come down to is about 15 to 20 pounds per foot. So what that does is it gives you the equivalent torque and drag of running 5-inch drill pipe, but you're actually running 9 5/8 liner. There are some unique scenarios where you have a larger liner and a very small inner string. Let's look at a 10 3/4 inch liner with a 2 7/8 inner string, and you can actually approach neutral buoyancy, or even very slightly negatively buoyant, when you've put the cement in place with like a 1.92 SG slurry, 16-pound slurry. But even in that scenario, we're talking about negative 1.5 pound per foot. So it wants to float with 1.5 pound per foot buoyant force, basically. And basically what that means is that each joint of casing is floating high side with about 60 pounds of up force. So if you can try and just visualize that, a range 3 joint of 10 3/4 inch casing weighing 20 kilos, 60 pounds. Like, I mean, most of us can lift that with one arm. So when you consider the beauty of that in terms of getting it installed and getting it cemented, it's massively profound. And the other beauty of FloatCure is that you can actually tailor the desired running weight based on inner string and fluid density. So if you want it to be a little less buoyant, you can use a different inner string, and that buoyancy is then taken throughout the cementing process, which is highly unique with FloatCure.
Great, thank you. Tyler, I think this one probably comes back to your presentation earlier, but what are the main lessons learned or things that could potentially go wrong with SeaCure, and how do you guys manage that?
Sure. Well, as far as lessons learned, there are quite a few that we could share concerning operations, but overall the system is quite simple, reliable, and robust. The service deployment history with 20 runs and 0 NPT is a testament to that. What I can say is that the main issue that we've seen in the past was related to the lockdown wiper plug version of the system. And that's just that a wiper plug got hung up in the cement head, which is an inherent risk associated with launching darts out of cement heads in general. But even in that instance, because of good contingency planning, the sequence of operations allowed us to deliver that SeaCure job with 0 NPT as a result. And since then, what we've done to rectify is to move away from an off-the-shelf wiper plug design to redesign the fins and the body. And since then, we've had 0 issues with that new design. And further to that point, what we can say is that we've had 100% success with the ball drop version of the system, which doesn't require the use of a cement head. And the other point to note is that our operations team provides bespoke running procedures and contingency plans and flow charts for all of our jobs as a way to help mitigate any of those kinds of issues.
Fantastic. Another question that actually came in throughout the your part of the presentation was, what's the additional rig up time versus the time savings that can be seen?
Tristan, would you
want me to take that? Yeah, sure. It's a nice question, Hugh. So with the 6 runs that we did with one customer, they were kind enough actually to share their previous 8 conductors that were done without SeaCure, so that we could do a really analytical side-by-side analysis. Now, normally, like you kind of intuitively estimate, it should take longer to run, the SeaCure thing at the bottom, because you've got an extra connection to make up. However, counterintuitively, it was actually found that we were around about half an hour per conductor quicker to install the inner string with SeaCure than it was for Poorboy. And when we did the thorough analysis as to why, it was because there's no need to manage the air gap, which is inherent with the Poorboy version of doing cementing, in the moon pool. which you normally do through screwing in the first and the landing string to the top drive, flushing and generating back pressure through the floats. And once you've got fluid coming through the ball valve, you've got somebody down there to go and close it, and then you've got to unscrew and then continue. That doesn't happen with SeaCure because you sting and stab with the inner string and the cart at the rotary table. It's a simple case of a 5-10 minute fill up with the casing fill up line. That's then finished. So counterintuitively, it's actually quicker to run SeaCure than it is a poor boy inner string.
Perfect. And then I think this one actually kind of came in at the same time, but what characterization has been done on the transfer of heat to the cement at surface to demonstrate that the surface cement has in fact been cured?
Yeah, I can take that one again. Yeah, so there's been a huge amount of work done with the University of Aberdeen in this thermodynamics department to create actually a bespoke algorithm, which has now been built into our proprietary SeaCure software based on very, very, very simple Fourier heat transfer, which has been with us as a human race for centuries and is very, very well understood. And so that algorithm is what computes the heat transfer through the cement, both at the shoe and all the way to the surface or seabed, I suppose, is wherever there's cement, we get a very, very granular pictures to exactly what the heat transfer profile is throughout that. Now, what we're able to then do is use those exact heat transfer curves to put and plot and put into a surface immersion heat bath. So we're able to take the exact cement slurry samples from the mix tub in the cement unit, put them into the immersion bath and follow the exact heat curves that the slurry experiences downhole, so that you can have full confidence that when you move towards slackening off the weight of the conductor, you have fully solid set cement.
Great, thank you. I hope you two don't mind, because as I say, we do have some more questions, but I am conscious of time and that some people probably are going to start dropping off. So before kind of that happens, I just wanted to say once again, thank you for everybody for taking the last hour out of your day to spend some time with Justin and Tyler here to hear more about the Cure technology line. As I say, we will kind of continue on with some questions just now, but yeah, just thank you once again. Okay.
Thank you, everybody.
So a question came in kind of towards the innovation section there, and they've asked, you make the point about buoyancy, but it's not clear how this will work when the hole is not completely horizontal.
Yeah, I can take that one. And the inclination of the well bore will lend itself to how difficult the string is to install inherently, or how much restoring force the centralizers offer to the string when cementing from a standoff respect. So, I think that the point being is that in not completely horizontal holes, how useful is float cure, and it's exactly the right thought process. What we're targeting with float cure is really challenging well trajectories, which are typically the ones closer to horizontal, namely ERD wells where you might be at 70-80 degrees for a long period of time, and trying to get the liners down is just nigh on impossible, let alone sort of rotate them for the cement job or get reasonable casing standoff for the cementation process. In a not completely horizontal application, if there still is a desire for float cure for whatever reason, of course that is absolutely fine to do. It might be for slightly different reasons in that scenario. Maybe you've got a very aggressive build from 20 to 50 degrees, for example, or 20 to 90 degrees, for example, and you just want less effective weight of your string to be able to make it through that aggressive build. Maybe that's a good application for float cure. So yeah, ultimately though, the buoyancy benefit being very, very simple Archimedes of the mass of the fluid you're displacing is what you experience up thrust wise. Not sure if that answers the question, sorry.
Next one, we've got a couple more. So will quick cure accommodate a conductor string with mixed sizes and wall thicknesses? And the example that they've given here is a 30-inch down to a 20-inch.
Yeah, sure, and I can answer that. And actually, yeah, we've actually done those quick cure jobs. So, you know, tapered string. I think the ones that the most aggressive we've done is 36 down to 30 down to 20. And the 20-inch by the 0.625 wall thickness that I can see there, the sort of 129, 130 ppf, we actually, those are the sort of things that we hold in stock. That's our bread and butter. You know, we do that day in, day out, actually. So yes, the answer is we can accommodate mixed sizes and wall thicknesses.
Mm-hmm. Another SeaCure one. So when discussing the SeaCure casing pressure test capabilities, you mentioned that there's a reduction in reliance on big bore packer in the event of test failure. How do you accomplish this? If a leak is detected during the casing test post-cement, is there still a need to hunt the leak using a big bore packer? It's a long question for you there, Tristan.
Yeah, good one, good one. And yeah, so it's a nice question, because actually one of the reasons that one of our remote location customers utilize the service is because they've realized that actually when using the ball drop version of our system rather than the wiper plug version, once you've cleaned and you've circulated and you've got a completely clean casing ID, you also leave a completely clean seal bore receptacle in the bottom. So that particular customer has actually said, you know, one of the reasons I really like SeaCure in remote location is that even in that very remote scenario that has been described there, of you get a, you know, a leaky casing pressure test post cement job, which we've never seen. But what you can do rather than with a big bore packer is you can actually run back in with your SeaCure latching adapter and a new set of seals on the bottom to go and utilize the existing seal bore within the chute. And that way you isolate that, and you can then, you know, you can re-pressure test something post cement job once the cement job's cured, or with a different fluid in the well bore to, you know, attempt to get that pressure test later on in the life of the well. Hopefully that answers that. But sorry, just to touch on that a little bit further, but one of the big reasons that big bore packers can be sort of, you know, less relied upon with SeaCure is because we do the pre-installation casing pressure test, which is there is no other way in the world to do it rather than SeaCure. You know, we actually pressure test the string when it's in auxiliary, completely made up, but yet to be cemented. If there was a leak at that point and you leak hunted it and identified it to a coupling, you can deal with it before you go and cement it in the well bore. So, you know, that's another reason why you're less reliant on big bore packers with SeaCure.
Great. We did have a question come in asking if there was a case study for FloatCure. Do you want to give us a bit of an update on where you're at with that technology?
Yes, and we have got a number of different customers that have requested you know, relatively advanced proposals for FloatCure and different applications across North Sea and further afield. There is yet to be a full-blown case study, but we are, you know, like I was mentioning, we use the exact same technology, the exact same system that we use day in, day out. It's a procedural difference.
Mm-hmm. Great. Someone else has asked, is there any thoughts on incorporating cement bond logging into the SeaCure inner string, especially for conductor and surface casing?
Yeah, it's a great question. Something that we've discussed in terms of replacing our weight set sub with some, you know, acoustic tool to take a little look out into the annulus. Not something that we've done yet though. But if whomever it was that asked the question, we would be glad to look at the application that you're considering in detail, and can work together for that.
Great. And the last one, which might be one to catch you off guard a little bit, but we've got one in that's asked, what applications do you see for land wells other than the ERD aspect?
Yeah, see that question there. Thanks for that one, Dave. Other than the ERD. Yeah, so for FloatCure, I'll separate it into FloatCure and SeaCure RS because I think those are the technologies that are relevant for land wells. FloatCure, obviously for high step out land wells, so yeah, you point to the ERD aspects already. If there is a desire to get, you know, perfect casing standoff, which is often the requirement for frac packs, for example. So if there are frac packs, being installed, and you need to get 90-95% casing standoff, and it's difficult to achieve that without this kind of technology, then that would be a great application. Salt squeeze, mobile salts have been known to collapse casings. There's been entire fields in the southern North Sea where they've lost every single 7-inch liner due to mobile salts, which is stemmed from either weak casing or poor casing standoff, where you get the point loading and the failure. So those can be good applications for the use of float cure to give you the perfect casing standoff and get reliable well integrity there. And that's kind of the float cure stuff, I'd say. SeaCure RS, wherever there is a cemented and perforated completion, SeaCure RS, what it offers is zero shoe track cementation, which is real useful for all wells, because you don't have to drill what would traditionally be the shoe track sump. If you wanted to go into a wellbore cleanup post cementation and you've already got a work string all the way to well TD, then SeaCure RS can present itself in that one. I see, Dave, there's a sort of, I guess, a follow-on question with that one. But I would suggest those being the sort of high-level reasons why customers might want SeaCure RS and float cure on land wells.
Great. Okay, I think we've covered all the questions. There for anyone who is still about, there were some questions that came in through the chat box that came directly to the panelists that we can kind of share the responses to as well. But I think that I just want to echo again, just a last thank you to everybody who's kind of taken time out of their day, especially, and stayed on later. And there's still quite a lot of you about. So if there's not any more questions, then I think that would be us.
Yeah, we really invite everybody to send us an email or drop us a line. Otherwise, to follow up with you directly if you'd like more information or if there's an application that we can look into for you with this technology.
Okay. So I think then nothing else seems to come in. So I think that's probably where we should draw this to a close. Thank you again, everybody. And I know that both Tyler and Tristan I've been delighted to have you here. So we will share the link to the recording as well, so you can access this later. And as Tyler's mentioned, the email address is on the screen there for you to contact both of them and speak directly about any questions that you might have. Thank you.
All right. Thank you so much.